In this video, we're going to look at finding the tangent line to a curve r equals 2 plus 2 cosine theta at pi over 4. So our polar curve looks like so. Pi over 4 is going to be this point right here, because if we drew a line from that point to the origin, we see we get about a 45-degree angle there, so that's theta equals pi over 4. This point here in polar is going to be pi over 4, and then when we plug pi over 4 into here, we're going to have 2 plus 2 times cosine of pi over 4. So we'll put this down here, 2 plus 2 cosine of pi over 4, but cosine of pi over 4 is rad 2 over 2, so 2 plus 2 times rad 2 over 2. So this is the point 2 plus rad 2. So all we need is the slope, and we'll get our tangent line, which we can see is going to look something like this, but we want to find the equation for it. Well, what we're going to do is treat these as parametric equations. These are our conversions between rectangular and polar. And what we know is that for this particular case, r equals 2 plus 2 cosine of theta. So I'm going to rewrite my x as 2 plus 2 cosine of theta times cosine of theta. And my y is 2 plus 2 cosine of theta sine of theta. And again, we're going to treat these like parametric equations. Well, to calculate a derivative in parametric equations, what we do is we're looking for dy dx. Well, we're going to do the derivative. We're going to look at dy, in this case d theta, over dx d theta. You might have seen these written with dt's before for your parametric equations. So what we need are the derivatives of each of these. Let's start with dx d theta, which is going to be a product rule. So I have 2 plus 2 cosine of theta times the derivative of cosine, which is a negative sine of theta, plus, now I'm leaving the cosine of theta alone, times the derivative of this guy. Derivative of 2 is 0. 2 cosine of theta is negative 2 sine of theta. Let's see if we can do much simplifying. So here, distributing that, we'll have a negative 2 sine of theta minus 2 sine theta cosine theta. Here, we're going to have another negative 2 sine theta cosine theta. So we can simplify just a little bit, and we get minus 2 sine theta minus 4 sine theta cosine theta. Not a whole lot more we can do with that, so let's leave it as is for now. Let's go ahead and find our dy d theta. Again, it's going to be a product rule on this guy. So I'm going to leave this part alone. 2 plus 2 cosine theta times sine theta plus, now, excuse me, we got to take the derivative of sine theta, which is cosine theta. My fault. I apologize. Now we'll leave the sine theta alone, times the derivative of this part, which we did here. We already know that's negative 2 sine theta. Excuse me. Let's see what kind of simplifying we can do. Right here, we're going to have 2 cosine theta plus 2 cosine squared theta. Here, we're going to have minus sine squared theta. And there's a 2 out front, sorry. Unfortunately, we don't have the Pythagorean identity. We could factor a 2 out, but because we're going to be evaluating that at a point, I'm not too worried about it. So my derivative for dy dx is dy d theta, as we saw up here. So 2 cosine theta plus 2 cosine squared theta minus 2 sine squared theta, all over what we found for dx d theta, which is minus 2 sine theta minus 4 sine theta cosine theta. Now, we know this is at the angle pi over 4. We know the point. We need to plug in pi over 4 for all of our thetas and see what happens. So I'm going to have to move this down here for a little bit more space. So let's go ahead and plug it in, and then we'll evaluate in the next one. Cosine of pi over 4 plus 2 cosine squared of pi over 4 minus 2 sine squared of pi over 4 all over negative 2 sine pi over 4 minus 4 sine pi over 4 cosine pi over 4. Now, this is one of our special cases, and cosine at pi over 4 is the same as sine at pi over 4. They're all rad 2 over 2. So let's plug those in and see what happens. So we get a rad 2 over 2 for this guy, plus 2. Now this time, rad 2 over 2 is going to get squared, minus 2. Right here, rad 2 over 2 is going to get squared again. That's the numerator. In the denominator, we have a minus 2 times rad 2 over 2 minus 4 times rad 2 over 2 times rad 2 over 2, 1 for each of these. I'm going to simplify it down here, and we'll go back up and write the equation. I kind of ran out of room. So 2 times rad 2 over 2 is just square root of 2. Rad 2 over 2 squared, that's going to be 2 over 4, or 1/2, times 2 is 1, so plus 1. This is going to be the same, so plus 1 minus 1. All over. Here we're going to have a negative 2 times 2 rad 2, so that's going to be negative square root of 2. And here, same thing, rad 2 times rad 2 is 2, 2 times 2 is 4. So this becomes 1/2, so negative 4 times 1/2 is minus 2. So when all the dust settles, we got a slope of 2 over negative rad 2 minus 2. And I'm going to factor out that negative. So negative rad 2 over square root of 2 plus 2 in the denominator. Well, look at our line. It makes sense that our slope is negative. Now we can put together our tangent line. We had the point, we have our slope. Putting those two together, our tangent line could be rewritten y equals our slope, negative square root of 2 over square root of 2 plus 2 times, we'll need our coordinate in rectangular, because we're doing the equation of a line. We can always convert it later. So we know that it goes through pi over 4. So that's going to be our angle, and our r is 2 plus square root of 2. So we're going to plug that in for our conversions. So the x coordinate is going to be, r is 2 plus square root of 2 cosine of pi over 4. The y is 2 plus square root of 2 sine of pi over 4, which those are going to be the same value, because cosine and sine of pi over 4 are just rad 2 over 2, which equals 2 plus square root of 2 times square root of 2 over 2. Now we can clean this up just a little bit, because I can distribute this. If I distribute here, I get square root of 2. If I distribute here, I get 1/2. Or excuse me, I get 1. So those are my x and y values. So I've got x minus square root of 2 plus 1, and then plus my y values, square root of 2 plus 1. So there is my tangent line. I've decided to do this as all exact values, but of course if we needed to, we could always get the decimal approximations.